Test. 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 A second here just to make sure that everything's working fine. How about now? Testing. Testing. The mic wasn't right setting. Not in the right setting. Try that. Okay, I think this might be good enough. If not, we'll adjust it during the stream here. Okay. Welcome to a live stream. Oh, we're gonna do a paper reading today, an actual deep dive. So not like the videos we had yesterday, which were more like figure reads. Here we're actually gonna deep dive because this is a very interesting paper. Dropout Reduces Underfitting. This is every now and then people release a paper which is not trying to push the state of the art or trying to show you some new model architecture. Every now and again, people will push a paper where they try to understand something a little bit more deeply, and they try to look into the black box that is deep learning and machine learning and try to understand things. So specifically in this paper, what they're trying to understand is dropout. And dropout is a technique that's been around for a while now, but it's basically this idea of, let me get a little neural net so that show this better, but you have a neural net that looks like this. And what you're doing when you're doing dropout is you're occasionally dropping out some of these neurons, right? So what does dropping out mean? Dropping out means that you basically make them zero. You make the values of them effectively zero so that the information that goes into them goes nowhere, and then the information that comes out of them is all zero, so it doesn't contribute at all. So it's kind of like if you were training a robot to jump and it had 4 legs, and then half of the time you were training it, you would tape one of its legs shut, and then you would tape one of the back legs shut, and then you would tape one of the front legs shut. So by disabling the neural network and kind of dropping out some of the neurons in the neural network, you prevent too much of the learning being focused on a smaller amount of the network, right? Because sometimes when you train a neural network, there will be one kind of neuron, one pathway through the neural net that ends up getting right or close to the right answer, and then all the gradients will continue to make that one little pathway through the neural net increasingly more and more and more prevalent. So you have this natural kind of pruning that is happening over time when you train a neural network, where the network is like reinforcing and digging a deeper and deeper groove on a specific path. And dropout, which adds this element of randomness and drops out specific neurons, makes it such that all of the neurons are used and that there's more of a diversity of pathways, and that the final kind of predictive power of the neural net is a little bit more general, a little bit more robust. So that's my terrible explanation of dropout, but luckily for us, we got this awesome paper here, and we're going to learn all about it, and I think they're going to actually explore even more complicated questions such as when to drop out. So over the course of training, are you dropping out the entire time, which is what they're calling here standard dropout? Do you have early dropout, late dropout? Maybe this is the beginning of a kind of dropout schedule, right? So mentioned before how, for example, learning rate has a schedule now usually. So you're changing the learning rate over the course of training, but uh, that's not really the case with dropout. People don't really have a dropout schedule, but it seems like maybe in this paper they introduced that as an idea and they show you that maybe it works super well. Hello, Dr. Prince. No. Okay, let's get started here. This is work coming out of Facebook AI Research, UC Berkeley, and then whatever MBZU AI is. Maybe that's a company or something, or maybe it's this guy's name. Fong Liu. I don't know. This is relatively recent work, less than a week old. And let's get into it. Introduced by Hinton et al. In 2012. So this is Jeffrey Hinton, very famous Toronto-based deep learning researcher. I think he was one of the 3 people who was awarded the prize, along with Jan LeCun and Joshua Bengio. Dropout has been stood the test of time as a regularizer for preventing overfitting. Okay, this is a nice way of summarizing what dropout does, where it prevents overfitting, prevents that kind of one path through the neural net that gets overused, right? In this study, we demonstrate that dropout can also mitigate underfitting when used at the start of training. During the early phase, we find dropout reduces directional variance of gradients across mini-batches and helps align the mini-batch gradient with the entire dataset's gradient. Okay, so it reduces the directional variance of the gradients across mini-batches. So mini-batches are, batch refers to a batch of data, and when you're training a neural net, you're not feeding the examples one by one. You're feeding them in batches, and the reason you're doing that is because a GPU, right, which is the hardware that underpins all of modern deep learning, the GPU is very good at doing matrix operations, right? A lot of simple operations at the same time. So if you were training on a CPU, then doing it one by one and doing it in batches wouldn't matter. But when you're doing it, when you're training on a GPU, being able to do entire batches of data in one kind of go is super fast, right? Super useful. So that's what they mean by mini batches there. This helps counteract this stochasticity. This is just randomness. It's another fancy word for randomness of SGD, so the gradient descent, and limit the influence of individual batches on model training. Okay, so influence of individual batches. Sometimes, right, when you're training, you're usually shuffling your data set, and each batch is composed of examples from your training data set in a shuffled kind of way. And sometimes you just so happen to get a bunch of examples of data that it pushes the parameters of the neural network, right, the weights of the neural network in a specific direction in parameter space that might not be beneficial towards your final task, right? So if you're training a cat and a dog or a cat dog classifier, right, something that classifies cats and dogs, you could imagine that every single batch of data, you would want there to be roughly 50% cats, roughly 50% dogs. But if you're just shuffling your data set, there might be individual mini batches where you're giving your model 50 examples of a dog, right? It's 100% dog examples. And you could see how a gradient update from a mini batch of entirely dog examples wouldn't be necessarily as good towards the final task of dog-cat classification. Findings lead us to a solution for improving performance in underfitting models. Early dropout. Dropout is applied only during the initial phases of training and turned on off afterwards. Models equipped with early dropout achieve lower final training loss compared to their counterparts without dropout. Then we explore a symmetric technique for regularizing overfitting models called late dropout, where dropout is not used in the earlier iterations and it's only activated later in training. Okay, so this is going to be the super interesting part paper to me, is not just dropout and what it does, because I think most people kind of understand at this point, but hey, what if we have kind of a dropout schedule? What does that look like? What is the results, and so on? Experiments on ImageNet and various tasks. Okay, so this is what they're going to be actually using to benchmark. ImageNet is not necessarily the best data set. I think it's a little bit dated at this point, but it is a consistent benchmark. So our results encourage more research on understanding regularization and deep learning. Their methods can be useful tools for future neural network training, especially in the era of large data. Yeah, so this should be interesting, is if they find that things like early dropout, late dropout, this kind of idea of dropout scheduling can increase the speed of training or reduce the total amount of training you have to do, I think that could be huge, right? Because training gets more and more expensive every year as people want to train bigger models on larger data sets. The year 2022 marks a full decade since AlexNet's pivotal image moment. So what they're referring to here is there was a competition in computer vision where people were basically trying to solve this classification task on ImageNet. And year after year, people came in with solutions, and they were just kind of classic computer vision solutions. And then in 2012, someone submitted a convolutional neural network to this ImageNet competition and kind of beat all the other ones out of the water. So ImageNet, AlexNet, 2012. I think there's an image that shows you kind of the step function improvement. Maybe here. I want to see the years before. Yeah, so I don't know if this is the exact one that I want or that I'm interested in, but this is basically what the ImageNet competition was. And you can see here 2010, it was roughly at 0.28 error, then 0.26 error. And then in 2012, AlexNet, right, this ConvNet, this one here, this is the actual model architecture of this ConvNet, suddenly beat everyone by a huge margin, right? It went from 0.26 to 0.16, which is huge, right? In these type of competitions, generally, you're playing for like a 1% improvement every year. So this was a huge drop. That's why they call it the moment, right? It's a historical moment for sure, which launched a new era in deep learning. It is no coincidence that Dropout also celebrates its 10th birthday in 2022. AlexNet employed Dropout to substantially reduce its overfitting, which played a critical role in its victory at the ILSVRC 2012 competition. So this is interesting. I did not know that AlexNet was one of the first ones to really employ Dropout. To me, the AlexNet ImageNet victory was mostly just based on the fact that they trained on a GPU and that they were using a convolutional neural net. But that's kind of where what I thought was the main contributor to their success, but it does seem like Dropout was a part of that. So maybe we've been overlooking Dropout and the importance it has. Without the inventions of Dropout, the advancements we currently see in deep learning might have been delayed by years. Dropout has since become widely adopted as regularizer to mitigate overfitting in neural networks. Randomly deactivates. Okay, so here's the actual formal definition of dropout. It randomly deactivates each neuron with probability p, preventing different features from co-adapting with each other. So probability p. Got mathematical definitions in the introduction. And what do they mean here? Preventing different features from co-adapting with each other. So you could see how, let's go back to a neural network image. Go. So if you're training this neural net and you keep feeding it examples and examples and examples, and this neuron here starts learning some kind of pattern and starts firing on that pattern. And then you have another neuron here that it's connected, right? All these neurons are kind of connected to every other neuron in the layer above and below them. You have another neuron here that starts to realize that, like, hey, anytime this neuron here fires, I'm also going to fire. And that turns out to be a really useful strategy for me as a little neuron to get good scores on the loss function, right? So you have this kind of co-adaptation where once there's kind of one path or one neuron that kind of seems to be onto something, other neurons will kind of mimic it and be like, okay, I'm just going to start getting I'm only going to be paying attention to this neuron here. I'm going to start ignoring what all these other neurons are doing because this neuron is the only one that really seems to be firing when it's doing something or correctly. So that can lead to this co-adaptation, which is you don't really necessarily want, right? Because you don't just want all of your neural net to be reduced to basically just a handful of neurons that are firing and every other neuron is just listening to those 2 or 3 neurons. So what you're doing in Dropout is you're going to randomly turn off some of these neurons, right? And what that's result in is that this neuron here, which is used to just listening to this neuron all the time, sometimes it's not going to be able to do that because this neuron is going to be dropped out. So it's going to have to figure out how to use the information from all the other neurons in order to get a good answer. Right? I'm kind of anthropomorphizing each individual neuron, that each individual neuron doesn't have agency in that sense, but every time you update the weights of a neural network, what you're really doing is you're saying how much is this neuron really I don't want to use the word attention because that is a formal definition too, but how much is this neuron paying attention to this neuron? How much is it paying attention to this neuron, right? Every single one of these lines is a weight parameter. So randomly deactivating each neuron with probability P will prevent different features from co-adapting with each other. After applying dropout, training loss typically increases. So, yep, this is important, right? When you actually put dropout, your loss is actually going to be higher than it was without it because you're kind of, it's like the analogy I was making of like a robot that has 4 legs and is trying to jump high, and you're like kind of disabling one of the legs. So it's actually going to jump worse, but then if you give it all 4 of its legs, it's going to jump better. So deep learning evolves at an incredible speed. Novel techniques and architectures are continuously introduced. Applications expand, benchmarks shift, and even convolutions can be gone. Okay, so they're making a little slight zinger at convolutions here being gone because vision transformers have largely taken over, but I think there's papers such as ConvNext that show you that convolutions can still be here and transformers haven't completely taken over yet. And we've also seen GANs make a comeback in one of the papers yesterday where people thought diffusion models were the future, and then now we see that GANs are making a comeback. But even though you have these back and forths with the architecture, Dropout has stayed. I think there was a period where Dropout was actually not popular. I will say I do kind of vaguely remember a point where it was kind of in fashion to have the belief that Dropout was a bad thing, that it kind of just slowed down your training for no reason and that you should actually not use Dropout. But I think since then, Dropout has become more and more standard practice. And maybe it'll go down again. Maybe there'll be a model architecture where Dropout doesn't really improve and then it kind of falls out of fashion, and then some new model architecture will come out where Dropout does improve and then it'll go back into fashion. So I think these different tricks in model architectures go in and out of fashion over time, right? For the curious, I'm drinking Yopon Holly, the only caffeinated plant in North America. Okay. It continues to function, including AlphaFold. Protein prediction, DALI 2 image generation. So, okay, so you see how Dropout's being used in kind of the latest and greatest models all over different types of modalities. Despite the sustained popularity of Dropout, its strength, represented by the drop rate P, has generally been decreasing over the years. The original Dropout work, a default drop rate of 0.5 was used. However, lower drop rates, such as 0.1, have been frequently adopted in recent years. So this is how many of basically the probability that each neuron can turn off. So if you have this little neural net and you have a dropout rate of 0.5, that means that roughly half of these neurons are going to be deactivated at any given point in time. If you have a dropout rate of 0.1, there's only going to be 10% of the neurons that are activated or that are deactivated at any point in time. Examples include BERT and vision transformers. I assume BERT and vision transformers have a dropout rate of 0.1. Primary driver for this trend is the exploding growth of available training data, making it increasingly difficult to overfit. Yeah, so something to think about here is that whenever Dropout initially came out, right, the data sets were smaller and the models were smaller. So you were basically training for many, many epochs, right? Where a single epoch is the whole data set. So you train, you feed all of ImageNet through your model, and then you feed all of ImageNet through your model again, and then you feed all of ImageNet through your model again. So you're basically training on the same data set over and over and over and over and over again. And the model itself isn't super deep. So it starts to overfit, it starts to memorize that data. And at that point, having something like Dropout, which prevents this kind of overfitting, is actually very useful. But nowadays, the data sets are so huge that the overfitting doesn't tend to happen, right? Because, or is not, it's always going to happen, but it doesn't tend to happen as much because the data set is just so huge that you're not just training on the same data set over and over and over and over again. It's like by the time you get to the end of the data set, there's just been so much stuff that the model kind of like almost forgets the first part of the data set. So overfitting is harder with larger data sets, so a regularization technique such as dropout that prevents overfitting is going to drop out of fashion, what I did there, as the data sets get bigger. Advancements in data augmentation, so things like right-left flipping, masking out things, brightness, contrast, perturbation, like there's different ways to do data augmentation as well. So other regularization techniques are kind of competing with dropout in terms of the best trick to use in a kind of a bag of tricks analogy. Algorithms for learning with unlabeled or weakly labeled data have providing even more data to train on that the model can fit on. As a result, we may soon be confronting more problems with underfitting instead of overfitting. This is kind of interesting, right? There's this kind of idea that maybe overfitting was a kind of common problem that we would run into when we were training small models on small data sets. But as the kind of deep learning and AI world moves forward in time, the data sets are going to be so huge. The amount of, especially these self-supervised kind of learning objectives where you're kind of like creating the data every time unique, right? Like every batch that you create is is coming from some kind of weird self-supervised pipeline. So it's different from every other batch that you've trained on. You're eventually going to get to a point where you can basically infinitely generate data. So you're always going to be underfitting instead of overfitting because you can't overfit to an infinite amount of data. Would dropout lose its relevance should such a situation arise? In this study, we demonstrate an alternative use of dropout for tackling underfitting. We begin our investigation into dropout training dynamics by making an intriguing observation on gradient norms, which leads us to a key empirical finding. During the initial stages of training, dropout reduces gradient variance across mini batches. This allows the model to update in a more consistent direction. Okay. These directions are also more aligned with the entire dataset's gradient direction. That's figure 1 here. Consequently, the model can optimize the training loss more effectively with respect to the whole training set rather than being swayed by individual mini batches. In other words, Dropout counteracts SGD and prevents excessive regularization due to randomness and sampling mini batches early during training. Okay, so what do they mean by that? So you have this drawing here of kind of this funnel, right? And this is a surface. It's a manifold on three-dimensional space. So it's a surface in three-dimensional space. And the reason it's three-dimensional space and this is a surface on that is because humans are very good at visualizing 3D space, right? And this surface, what it actually represents is the weights of a neural network, the parameters of a neural network. So neural network here, even this tiny little neural network here, right? This little tiny multi-layer perceptron that just has a handful of layers, every single one of these lines is a parameter, right? So if you think about how many lines there are, I don't know, there's probably 50 lines here, right? The if you wanted to represent if you wanted to create a visualization of all the weights of this little neural net here, you would need a 50-dimensional space, right? And as a human, it's basically impossible to visualize what a manifold looks like, what a surface looks like in a 50-dimensional space. So the best we can do is just pretend that our neural network only has 3 weights, right? Like three values for these little weights. It only has 3 connections. And then you can say any point on this cone is basically one possible value for the neural net, right? So this point here on this little cone represents one possible version of our neural net. This point here represents a different possible version of our neural net. This point here represents a different possible version of our neural net, right? And so on. And what they're showing you where the fact that this is a funnel is that Dropout kind of reminds me of something I read with regard to spline theory of deep learning. The idea, I think, that the ReLU activation makes it possible to view each layer as a set of input-specific feature spaces instead of unified feature spaces, given the firing of the ReLU. Yeah, so the neural net itself, right? There's going to be parts of the neural net that are only active depending on certain inputs. So if you have one input to your neural net, there's going to be some neurons that basically never fire when the input is one thing. And then there's going to be other neurons that only fire when the input is a different thing. So the actual weights that are in any part of this neural network are specific to the input, and gradients are only going to be pushed in those specific parts depending on the input. Going back to this though, I was kind of describing this, right? So what you're doing with gradient descent, right? Every time you train, we always kind of say pushing gradients, but what does pushing gradients really mean? What you're doing when you're pushing gradients is you're changing the values of these little weights, right? You're changing the values of each of these little connections. And what that means is that you're going from a point here and then you're moving into a different point, right? So you're moving around in model parameter space, right? And you're not just moving around in model parameter space, you're following the gradient. You're following basically the slope in model parameter space. So you can actually see here, that's what's happening. So you're starting here, you have a model, you initialized it, and then you feed it one mini batch, and you get the gradients, and you update all the weights according to those gradients, and then you move the model here. So now by updating the weights of the model, you've moved here, right? And then feed another mini batch and you take the gradients again. And then those gradients allow you to change the model weights again slightly. And then you move a little bit there, right? And because the mini batches are random samples from the actual data distribution, each mini batch is not going to be perfectly representative of the full data set, right? If you had a GPU large enough that you could feed the entire data set at the same time, you could do that, but you can't. You can only feed little samples of the data set, little mini batches of the full data set. So there's a little bit of noise in the fact that you're sampling mini batches at a time. So the path that you take through the model parameter kind of manifold here is not going to be perfectly towards the local minima, right? It's kind of be noisy. You're going to kind of move in this direction, and then the mini batch makes you move in this direction, and then it makes you move in this direction. So there is this kind of notion of like, if only we knew the direction of the entire data set, right? So this is what they're saying, that the entire data set has some gradient direction, right? That's what this green line is that if you could actually sit down and calculate the gradient for the entire data set, then you could take that direction and move in that direction and get to the endpoint faster, right? But you have to do it batch by batch, which means that you have to kind of take these like noisy steps, right? So they're saying without dropout, right, you're kind of moving a little bit more randomly, but with dropout, the directions are more aligned with the entire data set's gradient descent. So if you calculate the gradients for a mini batch, and that particular mini batch was evaluated with dropout, the resulting direction, the resulting change that you make in the model parameter space is going to be more aligned with the entire data set. At least that's what they're saying, right? So that is why here, these little gradient steps, right? Each of these arrows represents one mini batch, one gradient step is moving you faster towards the global minima, right? And what does this kind of like this like Sarlacc pit represent? Is that in the bottom of this Sarlacc pit, right, in the bottom of this minimum, if your neural net had this particular value for the weights, it would be better at your task. So this surface, this manifold, is going to depend on the task. A different task, every single task and neural net is going to have a different manifold like this, right? It's like anything you change is going to change the surface. So you can't know what this surface looks like beforehand. And there's all kinds of interesting work where people have like kind of plotted these surfaces or different types of neural nets, different types of problems. Generally, you can only do it with simple problems, but you can look at these surfaces and sometimes there's like there's kind of like sharpness and smoothness. See if I can find a good this neural net loss function smoothness surface manifold. There's like one paper that I remember. Yeah, this one here. Visualizing the loss landscape of neural nets. So this is just like a little like a toy problem, right? Like a theoretical, just like a mental model, right? But the lost surface, the lost surface of a neural net is actually much more complicated, right? It looks more like this, right? And in this paper, they were showing you how the lost surface, right, for a neural net. So like you're going to be doing the same thing. You're going to start at a little point, and then every mini batch, you're going to be taking a step, right? And you want to get to the lowest point in this landscape. So you can imagine how it could be a lot difficult to find the lowest point if your loss surface is actually very complicated, right? So maybe you start here, right? You start here and then you take the mini batch and the mini batch is telling you, okay, the gradient says go that way. So you walk here and then it says, okay, well now the gradient says go this way. So you walk here and out here and then here. So like the path you're going to be taking here is a lot more complicated than something like this. In a ResNet, right? Whenever you have residual connections, the loss landscape becomes more smooth. So that's cool. And actually the coloring, these might even be the same people. Is this the same people? Who wrote this paper? Analyzing the lost landscapes of neural nets. If it's the same people. Yeah, so this is the paper that I'm talking about, which is pretty good. I do recommend this paper. Have the time. Hao Li, Sheng Zhu, Gavin Taylor, Christoph. Sheng Zhu? Wang Liu. Okay, so I don't think these are the same people, but very similar looking plots, right? Like, look at that. Look at this plot. Look at the coloring. They use the same program, but this is more what a realistic landscape, realistic manifold would look like. Okay, we're getting kind of stuck on that. I feel like we're going to take forever to do this paper if we don't move a little faster. So let's move a little faster here. Based on this insight, we introduce early dropout. Dropout is only used during early training to help underfitting models fit better. Early dropout lowers the final training loss compared to no dropout and standard dropout. Okay. So I think final training loss, they probably mean the loss at the very, very end. Conversely, for models that use standard dropout, we propose to remove dropout during earlier training periods to mitigate overfitting. We refer to this approach as late dropout. Demonstrate that it improves generalization accuracy for large models. Okay. So I wonder how late that is. I wonder if you could do dropout in fine tuning as a method of improving generalization and reducing catastrophic forgetting. We evaluate early and late dropout using different models on image classification and downstream tasks. So they're doing ImageNet, of course. So ImageNet is an image classification benchmark. Our methods consistently yield better results than both standard dropout and no dropout. We hope our findings can offer novel insights into dropout and overfitting and motivate further research in developing neural network regularizers. Revisiting overfitting versus underfitting. Okay, so now they're going to think more deeply about what does overfitting and underfitting actually mean. Overfitting occurs when a model is trained to fit the training data excessively well but generalizes poorly to unseen data. Yeah, so nice little definition. The definition that I use all the time is memorizing, right? So you can think of overfitting as the model memorizing the data set. Right? It's constrained to the data distribution that it's trained on. The data that you train on has some distribution. And when you are overfit, your model is very, very good at predicting within the bounds of that distribution that you've been training on, but it becomes increasingly worse and worse at predicting outside of the bounds of that distribution. The model's capacity and the dataset scale are amongst the most critical factors in determining overfitting, along with other factors such as training length. Larger models and smaller datasets tend to lead to more overfitting. Yeah, so one thing that people will mention sometimes is this notion of model capacity. So there's this idea that the model has like a certain capacity. It means that the bigger a model is, the more capacity it has, the more ability it has to kind of store the information in that data set within the weights, right? So worst case scenario, you have a very, very large model and a very, very small data set, at which point the model has more than enough capacity to basically memorize every single instance in the training data set. And it used to be the case that when you had these smaller data sets, people would purposefully make the model smaller because the smaller models wouldn't overfit as much, right? And you would have a better, more generalized model. But I think nowadays the idea of making a smaller model to make a more performant model is actually I don't think anybody's going to do that, right? I think at this point the models are as large as they can physically fit them on a GPU, and as large because the data sets are just so big that they're more worried about underfitting, right? As this paper was mentioning. We conduct several simple experiments to clearly illustrate this trend. First, when the model remains the same but we use less data, the gap between training accuracy and test accuracy increases, leading to overfitting. Figure 3, top, demonstrates this trend with VIT tiny 32. So this is a vision transformer. 32 refers to the number of patches, I think, that is being used as part of the vision transformer, right? Because a vision transformer treats an image as a sequence of patches. Trained on various amounts of ImageNet data. Second, when the model capacity increases while keeping the dataset size constant, the gap also widens. So when the model capacity increases, what all that means is that the model's getting bigger. So model capacity increases just means bigger model. Illustrates this with VIT tiny, small, and base. So these are 3 different sizes of transformers. You have a tiny one, a small one, and then I guess base is bigger than small and tiny. Train all the models with fixed 400 iterations. Let's actually do that. 4,000 iterations without data augmentations. All right, so what does overfitting look like? You have accuracy here, and you have test accuracy. So this is going to be how good your model actually is, right? The test data set is held out. So the model isn't seeing the data in the test data set. It's only seeing the data in the trained data set, right? So here's a better example of this. But when you have a very high accuracy on your train data set, but a very low accuracy on your test data set, that means your model is overfit, right? That means that sorry, your model has effectively memorized the training data set, and it's very, very good at predicting on the training data set, but it doesn't actually understand, doesn't have a good model, it doesn't have a good concept, it doesn't have an actual understanding of the problem itself. It just basically just memorized your training data set, and you can see that because the performance on the test data set is significantly worse. So the difference between the train and the test here is kind of a gauge of how much overfitting is happening. And what they're showing you here is different size models, right? So you have VIT tiny, not really overfitting at all, right? It has roughly the same performance on train and test, even if both of those performances are kind of shitty. You can see how as the model gets bigger, right? Bigger model capacity, right? Capacity increases, you're going to overfit more. So here in the top one, they have amount of ImageNet trained data. So this is the size of the data set. So here they're saying, how does overfitting change when you have when you increase or decrease the model capacity, right? When you make the model bigger or smaller. And here they're saying, what does the overfitting, underfitting look like if you change the amount of data? So you can see that when you have a small amount of training data, you're going to overfit a lot easier. So look how bad this overfit is. You have a score of 99.9% on the trained data set, and then a score of 5.4 on the test data set. So this is overfit hard right here, right? So if you have a tiny data set, you're going to overfit a lot. The bigger your data set is though, right? So this is 100% of ImageNet data, which is a bigger data set, and they're keeping the model size constant here in this top part. You're going to see that the overfitting is not as bad, right? 45% on the training data set versus 32% on the test data set. So this is a much more reasonable amount of overfitting. All right, dropout. We briefly review the dropout method. At each training iteration, a dropout layer randomly sets, sorry, sometimes I don't realize that my head might be in the way of the text, so let me know. We briefly review the dropout method. At each training iteration, a dropout layer randomly sets each neuron to 0. Okay, this is setting it to 0 is effectively dropping it out, right? During inference, all neurons are active but are scaled by a coefficient to maintain the same overall scale as in training. So what does that mean by that? So if you have your little neural net, right? Going back to our little neural net, and during training, you have something like a 50% dropout, which means that during training, this little neuron here is only going to be looking at the activations from 3 neurons, right? So if you're doing this during all of training, this little neuron here is used to only seeing the activations of 3 neurons. If then during inference, right, so inference is when you're actually using your model to do something versus training, you're just kind of training it. If during inference you now don't have any more dropout and now you have all of the neurons activated, that's just going to be so much signal, right? Like you're just like pushing so much more crap. It's like you're taking a pipe that is normally has a certain amount of water coming in through it, and then you're doubling the amount of water that's going in through it, right? So this little neuron would just be flooded, right? It would just constantly be activating because the signal coming from 6 neurons would just be so much stronger than the signal coming from 3 neurons. So what people do is they'll scale it. So when they actually do inference, they'll scale the output of the neurons based on how much dropout they were doing in training, just so that the neurons aren't like kind of like flooded, I guess is the analogy that I'm using here, right? too much signal. As each sample is trained by a different subnetwork, there's so much for me to kind of go on here. We're going so slowly. So in the original Dropout paper, which I think they reference here, it's like a 2012 Dropout paper. One way that they try to explain what Dropout is doing is they introduce this concept of subnetworks, that what you're doing when you're training Dropout is you're really training a bunch of little subnetworks or submodels at the same time. Let's see if we can actually find, there's an original Dropout 2012 Hinton. This one? PDF, give me PDF. There's an image in this. Yeah, here you go. So this is a little neural net, and then you have the neural net with the dropout, right? So during training, you're going to drop out some of these neurons. So one way that they described dropout in this paper is that really what you're doing is you're training an ensemble of subnetworks, right? Where you're not training one neural network, you're training this kind of like ensemble, which means many. Ensemble just means together in French, right? You're training many little neural nets all at the same time. So when you perform inference, it's almost like you're doing like a mixture of experts. Well, that has specific terminology too, but it's basically you're asking a bunch of little individual subnetworks what the answer is, and the final answer is the combination of those. Right, so this is kind of what they're describing here. In implicit ensemble of exponentially many models. I don't know about exponentially many models. There's a finite amount of permutations of possible dropout configurations. So I guess as you increase the model size, the total number of possible subnetworks will also increase, probably exponentially. So that's maybe what they're referring to there. But I do like this this kind of way of thinking of dropout as basically just you're doing an ensemble of subnetworks. I'm actually going to, let's replace this random Google image search with this one. I don't like it. I feel like this is a better example, better thing. Okay, stochastic depth. So stochastic, again, just fancy word for random. Various efforts have been made to design dropout variants. Okay, so of course, with any kind of deep learning architecture or deep learning trick, as soon as you push it out and you get some success for it, there's going to be a whole squad of academic researchers who are going to try to figure out some little change they can make, some little variant of your technique, and kind of test it out, right? So over the years, obviously this paper came out in 2012, so here you see 2013, 2014, 2018, 2016, 2016. So people have been trying different types of dropout, different variants, different ways of using it, and seeing if they find anything that works well or not. And one of the things that they did discover is, I guess, stochastic depth, or SD, which is designed for regularizing residual networks. So residual networks is residual connections. We've covered them on the channel before, but basically, if you can imagine that there was you see how all these arrows here, they only go to the layer above them, right? They only go one layer up. So a residual connection, or sometimes also called a residual pathway, is if you had one of these arrows and it actually went all the way around and it went to the next layer up, right? And it could go even higher than that and higher than that. And if you transformer paper, right? And in more modern deep learning architectures that are more complicated, you have very intricate kind of residual connections. So you can see here, this connection here, this is a residual connection here. You see how it skips this layer here and it just goes straight up to the layer on top. Here you have another residual connection and it skips this multi-head attention and then goes up to this layer up here. So residual connections, right, go all the way, can skip layers. So I guess stochastic depth here is basically a type of dropout that works for residual connections. And the way it works is for each sample or mini batch, the network randomly selects a subset of residual blocks to skip, making the model shallower and thus earning its name stochastic depth. Okay. Randomly selects a subset of residual blocks to skip. So much like you zero out individual neurons, you would zero out individual residual connections. And then because the residual connections, you can think of them as making the model deeper, right? And shallower. You could call it stochastic depth because you're changing the depth. You're randomizing the depth of the neural net. Commonly seen in modern vision networks, including DEET, ConvNext. So this is actually the paper that I referenced. That's interesting. So they reference ConvNext here, which shows that convolutional neural nets still have a place in the modern world of transformers. But then up here, they say convolution can be gone. I don't know. It seems weird, right? Because to me, ConvNext is like the example, the proof in the pudding that convolutional neural networks aren't completely dead yet. Several recent models use SD together with dropout, since SD can be viewed as specialized dropout at the residual block level. The term dropout that we use later could also encompass SD depending on the context. Yeah, so this is sometimes a problem with these kind of understanding papers and theory type papers where they try to understand something where it's limited to the architecture and the benchmarks that they decide on, right? So like the findings that they find in this paper might not necessarily be applicable to other types of dropout. But here they're saying, you know what, maybe they are. Maybe even though we don't really mess with stochastic depth, which is a type of a variant of dropout, we're somewhat certain that the conclusions that we come to in this paper could also be applicable to stochastic depth. Drop rate. Probability of setting a neuron to 0 in the dropout is referred to as the drop rate P. Hugely influential hyperparameter, right? So it's a probability between 0 and 1. As seen in swing transformers and ConvNext, the only training hyperparameter that varies with the model size is the stochastic depth drop rate. Okay, we apply dropout to regularize the VITB model and experiment with different drop rates. Okay. Tell me what the best drop rate is, even though I bet you that the best drop rate is going to change depending on your problem and depending on the model that you're using, right? Just like any other hyperparameter, it unfortunately, the value or the best value for it will change depending on your application. Setting it too low does not effectively prevent overfitting, whereas setting it too high results in overregularization and decreased test accuracy. In this case, the optimal drop rate for achieving the highest test accuracy is 0.15. Okay, so they found a 0.15 dropout as the best one here. So you can see here different amounts of dropout on the x-axis. You have everything from 0 to 0.25. Then you have the accuracy. So you can see with a dropout rate of 0, right, no dropout, you have really bad overfitting. At 99% on train, 31% on test. This is super overfit. But as you kind of go higher and higher with the dropout, yes, you're reducing the overfitting, right? You can see here how this one is not overfit at all, but you're also reducing the score on your test data set, right? And at the end of the day, you want the best possible model for your test data set. So this number here is the one that you really want to make the highest amount possible, right? 37.1 versus 31. Your training accuracy is actually irrelevant. You don't care how well the model does on the training data set. What you really care is how well the model does on the test data set. Different model architectures use different drop rates, and the selection of optimal drop rate P depends heavily on the model network. Yeah. Selection of optimal drop rate depends heavily on the network model size and dataset size. So not only that, but it's also going to depend on the type of task that you have, the type of loss that you have, how much data you have. Like there's so many variables here that when you're doing your hyperparameter sweeps, if you're training your own model, you're going to want to sweep over a couple different drop rates in order to find the drop rate that works best for you. We perform a hyperparameter sweep for drop rate intervals of 0.05 for each setting. From figure 5, we observe that when the data is large enough or when the model is small enough, the best drop rate is 0, indicating that using dropout may not be necessary and could harm the model's generalization accuracy by underfitting the data. When the data is large enough or when the model is small enough, the best drop rate is 0. Interesting. I don't know if I agree with that. I think that, to me, even a very small drop rate of like 0.0 something, 0.05, right? It's like, I feel like you always win by having even just a tiny bit of dropout. Optimal drop rate, training with a larger data set or a smaller model. So this is similar to the figure that we saw here, where they're going to be changing the amount of data. So this is showing you when you change the amount of data, how does the drop rate, where does the optimal drop rate sit? And then here, if you change the size of the model, where does the optimal drop rate sit? So when you have a small amount of data, you want to use larger drop rate. When you have a large amount of data, you want to use a smaller drop rate. When you have a big model, you want to use a larger drop rate. And when you have a small model, you want to use a smaller drop rate. In the literature, the drop rate used for dropout has generally decreased over years. Earlier models such as VGG and GoogleNet had very high drop rates of 0.5. VITs use a moderate rate of 0.1. Recently, large language models and self-supervised vision models, so this is going to be Clips, I think Clip is maybe the main one, do not use dropout. This trend is likely due to the increasing size of data sets. Model does not overfit easily to very immense data. With a rapidly growing amount of data being generated and distributed globally, it is possible that the scale of available data may soon outpace the capacities of the models to train. While data is generated at the speed of quintillion bytes per day, I did not know that. We are apparently generating 1 quintillion bytes. Hey, that is crazy. Models still need to be stored and run on finite physical devices. Given such a contrast, future models may have more trouble fitting data properly than overfitting too severely. As our experiments above demonstrate, in such settings, standard dropout may not help generalization as a regularizer. Instead, we need tools to help models fit vast amounts of data better and reduce underfitting. How dropout can reduce underfitting. In this study, we explore whether dropout can be used as a tool to reduce underfitting. To this end, we conduct a detailed analysis on the training dynamics of dropout using a proposed tools and metrics. We compare two VIT16. So this is the models that they're using, right? VIT tinies with 16 image patches on ImageNet dataset. One with dropout as the baseline and the other one with a 0.1 dropout rate throughout training. Okay, so the baseline here is going to be no dropout. That's going to be this dotted line here. It's going to be no dropout. And then the one with dropout only has a 0.1 dropout, so it's still relatively small dropout. Begin our analysis by investigating the impact of dropout on the strength of the gradients G. Got a little mathematical definition going here. G, measured by their L2 norm, G. So gradient G, what does that mean? It basically means this, right? You could think of basically this little arrow here as representing a single gradient step in model parameter space. So the L2 norm of the gradient, kind of think of it as roughly kind of the length of this vector, right? That's one way to kind of think of it. For the dropout model, we measure the entire model's gradient, even though a subset of the weights may have been deactivated. As shown in left, the dropout model produces gradients with smaller norms, indicating that it takes smaller steps, right? Smaller norms, smaller steps, right? So if you have a smaller gradient norm, these little arrows are smaller, which means you're taking smaller steps. So you see here how the little arrows are smaller in magnitude. So this gradient step is bigger, right? You're going from here, your weights might be one value, and now they're very different values. But when you're taking a small step, your weights are here, there are some value, and now they're only a very slight difference in those values. Okay, so gradient norm left and model distance right. Here they're comparing the gradient norm. Again, smaller one there is a smaller jump. So you can see that with dropout, the size of the little vectors, right, in that Sarlacc pit visual is smaller, but just barely so. You know, it's really not that huge. I would have liked to see dropout 0.1 and then maybe dropout 0.4, dropout 0.8, right? See how those compare. And then model distance. Model distance mean. Okay, well, actually, here you go. This is what they say. Since the gradient steps are smaller, we expect the dropout model to travel a smaller distance from its initial point than the baseline model. To measure the distance between two models, we use the L2 norm, represented by W1 minus W2, where Wi denotes the parameters of each model. Okay. So 1 Wi denotes the parameters of each model. So what do they mean by that? So remember how we said that each of these little arrows here is a weight, right? So a weight matrix is basically a matrix that has all of the values of these little arrows. And what you're doing when you're training a neural net is you're changing the values of these little arrows, right? This little arrow might be 0.5, and then you make a gradient update and it changes to 0.4, and then you make another gradient update and it changes to 0.3. And you make a big gradient update and it changes to 1.7 or something weird, right? So the change in the values of these little arrows, and it's not like they're changing direction, right? They're just changing strength. So one thing you can do is you can measure how much the gradient step is, right? How much are you changing all these little weights? But another thing you can do is just simply say, okay, well, I have my neural net at one point in time during training, and then I have my neural net at a different point in time during training. I'm just going to subtract the L2 distance. I'm going to find the distance between all the weight values in this neural net and all the weight values in the neural net at a later point in time, and that's roughly what they're doing here, right? W1 minus W2. And that's going to give you some rough idea of how different the model is to each other. It's the distance in model space. However, to our surprise, the dropout model actually moved by larger distance than the baseline model, contrary to what we initially anticipated based on the gradient norms. So this is actually interesting here. So actually, before I go into my shitty analogy, let's see what their shitty analogy is. Let us imagine two people walking. One walks with large strides, right, big gradient steps, while the other walks with small strides, small gradient steps. Despite this, the person with the smaller strides covers a greater distance from their starting point over the same time period. Why? Right? This might be because the person is walking in a more consistent direction, whereas the person with larger strides may be taking random meandering steps and not making much progress in any one particular direction. Okay, I like that. That's actually a very good little analogy, right? Where when you don't have dropout, your gradient steps are bigger, but when you compare the model at some point in time here and then the model at some point in time here, the total amount of distance traveled, right? The difference between the weights at model 1 and the weights of model 2 are actually not that far. And even if you take smaller gradient steps, as is the case here in the with dropout, you can travel a farther distance, right? Because it's more consistent. And thus the difference between the weights at 1 and the weights at 2 are going to be higher. Actually, this is I do like this analogy. This is a very nice little analogy here. Gradient direction variance. So variance, right? Change. How much variance, how different are things, and then how different are the gradient directions. So high gradient direction variance means the gradient's kind of like all over the place. Low variance in the gradient direction means the gradient's kind of generally always pointing in the same direction. We hypothesize the same for our two models. The dropout model is producing more consistent gradient directions across mini batches. Test this, we collect a set of mini batch gradients G, have some set of little gradients. By training a model checkpoint on randomly selected batches, we then measure the gradient direction variance, which they're calling GDV here, by computing the average pairwise cosine distance. Average pairwise cosine distance. Okay, so you have two vectors, right? You have a set, you have GI, which is one gradient vector, and then you have a different gradient vector, GJ, right? And both GI and GJ are part of a set of vectors, capital G. So GI and GJ are taken from a set of vectors, capital G. That's what this means here. And then this comma I does not equal to J. What that means is that we're not going to do this if the gradient vector is the same. So you have 10 gradient vectors. You're not evaluating this cosine distance between the same gradient vector. You're only going to be doing it for the pairs of vectors that are different, right? So that's, you're summing over all of that. You're summing over the cosine distance, which is this equation here, right? It's the product of these two vectors here. I think that's inner product math equation or notation. Math notation. Yeah. So when you see this little caret, one thing, comma, other thing, caret, what that means is the inner product. So that's this here, right? Inner product of GI, GJ over the magnitude of GI and GJ, and that's the distance. So for vectors that are further apart, going to be bigger. Vectors that are closer together, going to be smaller. And here you have the gradient of G, or not gradient, the magnitude of G, magnitude of G minus 1, 2 over that. And this is going to give you the gradient direction variance, which is going to basically be a measure of how different the gradient directions are. Right, so you can imagine that the GDV is going to be much higher for this than it is going to be for this. L2 norm doesn't consider that the step length might still be the same in the directions that wasn't dropped out. L2 norm, step length might be the same, the directions that weren't dropped out. All right, Theo, I'm thinking about your question. Suppose the whole step can still be considered though. So yeah, actually that is a good point, right? That in some of the dimensions of your model parameter space, the gradient is going to basically be 0, right? Because if for this little neuron here, right, you zeroed it out, which means that there's going to be no gradient update for this neuron, right? So you are correct there, Theo, that the L2 norm is kind of tricky to think about because the L2 norm of a smaller amount of neurons, right? If this one changes by 0.1, this one changes by 0.2, and this one changes by 0.1, right? Isn't that going to be smaller than if you had this one changing by 0.1, this one changing by 0.2, this one changing by 0.1, this one changing by 0.2? Like, wouldn't you get a bigger vector by doing that? So I think your intuition is correct there. So the rest of your question is the L2 norm is just smaller because some directions are 0. Yeah, I think you're right. I think that's the case. I think that the reason why it's probably smaller is because some of these neurons aren't changing, which means that when you add up all the changes in the weights and do the L2 norm, right, which is basically just summing them together and squaring them, then you're going to end up with a smaller number. So I think you're correct there, Theo. Thanks for the questions. Okay, let's keep going. As seen in figure 7, the comparison of variance supports our hypothesis. Up to a certain iteration, approximately 1,000. So iteration here refers to the total amount of training steps, right? And each training step is a mini batch. So after 1,000 mini batches, right, The dropout model exhibits a lower gradient variance and moves in a more consistent direction. So it's important to note here that there's nothing magical about 1000. The number 1000 is going to heavily depend on the model that you're using and the data set that you're using. So there's nothing sacred about this 1000. Definitely don't randomly decide on stopping dropout after 1000 in your particular problem. Figure 7, gradient direction variance. The model with dropout produces more consistent mini-batch gradients during the initial phase of training up to approximately 1000 iterations. Gradient direction variance. So you have the baseline and then the dropout, which has a 0.1, of course. You see here how the dropout model seems to have consistently lower variance in the gradient direction, but it's actually not necessarily huge, right? There's definitely points in time here where the baseline model has a more consistent gradient than dropout. One thing to consider here too is that as soon as you push, right? So like if they initialize these models to the same thing, then here and here the models are the same. But as soon as you push one gradient step, this model and this model are now different, right? So you have two different, you might have the same model here, but then here you have a different model. And the relationship between the random mini batch and the model weights is going to produce like a different gradient step, right? So one thing to think about it here is that the gradient at this point here after one step is going to be different than the gradient at this point here after one step. And here it doesn't really seem like it matters because the way that this loss surface is shown, it's very consistent, right? It's just this kind of like consistent funnel that goes down into the same space. But normally the loss landscape looks a little bit more complicated. It looks like this, right? So you can take a gradient step and end up lucky, right? You could take a gradient step and end up here, and then now you're just very close to you could just take one more and end up there. So it's going to be noisy, right? Like sometimes you're going to take gradient steps and you can take a better gradient step by doing something incorrectly. And it just so happens to be that way, right? So that's what I think is kind of happening here, right? Where you see suddenly here, there's a gradient step that the baseline model takes that is like way better, right? It's like, oh shit, it just found a consistent little slope, right? And what that means is that it found some area of the loss landscape that happens to have like a very consistent and smooth gradient downwards, right? Versus like if you're here in this part of the loss landscape, this part of the loss landscape is so noisy that your gradient direction variance is probably going to be very high because you're going to be taking a step here, and then you're going to be taking a step here, and then you're going to be taking a step here. So the loss landscape itself is going to determine or at least influence heavily the variance in your gradient directions. So something to think about with that. Question remains, what should be the correct direction to take? With the training data, the underlying objective is to minimize the loss on the entire training set, right? This is what we were saying. So ideally, if we could feed the entire training data set all at once in one giant batch, that's what we would do. We compute the gradient for a given model on the whole training data set, where dropout is set to inference mode to capture the full model's gradient. Then we evaluate how far the actual mini-batch gradient, G step, is from the whole data set ground truth gradient. Okay, so you cannot calculate the ground truth gradient for anything realistic, right? Like you're only going to be able to do this for very small neural networks and very small data sets. So it's not like you're going to be able to find the ground truth gradient for your problem. So here they're just using it as kind of like a theoretical like kind of talking point, but there actually wouldn't be a way for you to calculate this like entire whole data set ground truth gradient. But for their kind of like small toy problem here, this kind of like theoretical paper, it's useful for them to be like, okay, well, let's actually kind of like zoom in super hard and see how far away is each little gradient step from the ground truth gradient, right? So I need to like duplicate this paper just so I have this image here, but you can see this is the green is going to be the whole data set gradient here, right? So this is the quote unquote ground truth gradient. And then the little black arrows are the mini batch gradients. So these are the gradients for each mini batch, which is a subset of your entire training data set. So what they're going to be doing here, probably in this equation, is basically just how much alignment is there between those. And they use, again, the cosine distance, right? So one way to think of the cosine distance is basically like this, right? It's like the more those vectors are together, like the more they are aligned and pointing in the same direction, the angle between them, right, is going to be smaller and smaller. So that's really what the cosine distance is doing. It's just that the cosine distance is doing that in probably some super high dimensional space. So as a human, it's basically impossible to visualize what the angle between a 512 dimensional vector and a 512 dimensional vector means, right? Our human brain just can't visualize that amount of dimensions. So we always kind of project everything down into 2 dimensions or 3 dimensions because we can visualize 2 dimensions and 3 dimensions. So it's just important to realize that like in these types of pictures, everything is 3-dimensional or 2-dimensional, and you can look at these angles and you can look at these gradient steps and be like, oh, okay, it's moving here and here and here, and this is the whole gradient steps. But like in actual real world deep learning, you can't actually, you don't know what this says, right? This is like 512,000 dimensional space. Like you're talking about steps, vectors, 1,000-dimensional vectors. Like we don't actually know if the surfaces look like that, right? We don't actually know if this is a good representation, a good visualization of what a lost landscape looks like in a very high dimensional space, and what a gradient step looks like in a high dimensional space, and what a gradient direction looks like in a high dimensional space. So important to realize. But basically, they're doing the same thing here. They're looking at the global ground truth gradient, whatever they're calling, and the distance between the g hat, which is the ground truth, and then the individual steps that are part of this set of gradient vector updates, g. We calculate this error and plot in figure 8 at the beginning of training. The dropouts mini batch gradients have smaller distances to the whole data set, indicating that it is moving in a more desirable direction for optimizing the total training loss. After approximately 1,000 iterations, however, the dropout model produces gradients that are further away. This could be the turning point where dropout transitions from reducing underfitting to reducing overfitting. Interesting. Okay. So there seems to be some point in training at which the dropout model ceases to give you a more aligned gradient step to the theoretically optimal gradient direction, right? So here in the beginning, the dropout model is the gradient updates that it gives you over the model parameters seem to be better aligned with the actual theoretical like whole data set gradient direction. So look at that, it just keeps getting more and more consistent, keeps going down, 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 down. The gradient error, which is kind of this alignment between those, is low. But then there seems to be this point at which the baseline model actually starts to be more aligned with the theoretical optimal gradient direction. And then the dropout itself, or the model with the dropout, has more random gradient steps compared to the theoretical optimal gradient step. So I don't know. I don't know if this is something that's going to happen with every data set and every model and every type of training paradigm. I suspect that's not necessarily the case, but I don't know, maybe. The experiments use VIT optimized with Atom W. This is a optimizer. We observe similar trends when using other optimizers such as SGD and Momentum SGD or other architectures such as Swing Transformer. So one important thing to think about here is optimizers deep learning GIF. So right here in this paper, oh shit, I said it, but we seem to be saying, we have this idea that, okay, we have the model, we evaluate the mini batch, we get the gradient, and then we simply move the weights in that direction of that gradient. But this gradient step, there's actually a lot of like work that people have done on optimizers, right? Which is basically the function and kind of process by which you take this step. And there's different optimizers, and they have all these extra terms like momentum and stuff like that. And this. So there's one GIF in particular that I like. Let's see if I can find it. Yeah, here. So you can see here, I love this. Shit. I love this chart. But here you can see, so this is a loss landscape, right? It's like a contour plot of a loss landscape, and you can see how these are different optimizers. So SGD is kind of like the most vanilla version, right? It's basically what you see here. This is SGD. But something like RMS prop, Attograd, Atom, like you can see how they have, because of these momentum terms, because of this kind of like additional stuff that people into them, they don't necessarily take the gradient step every time. They'll like modify that gradient direction that's being given to them by the mini batch, and then kind of like momentum is kind of the easiest one to think about. But you can see here how they result in a different path, right? And this is again, it's like a loss landscape, or you can think of every point on this manifold as being a single model. So every time these little balls move, that's one gradient step, one mini batch. So this is showing you training over time. Okay. Get back to it. So bias variance trade-off. This analysis at early training can be viewed through the lens of bias variance trade-off. For no dropout models, an SGD mini batch provides an unbiased estimate of the whole dataset gradient because the expectation of the mini batch gradient is equal to the whole dataset gradient. Maybe. I mean, I don't know. I would say that the mini batch, because it is randomly sampled, does not actually represent the true training data set distribution. So just because you're sampling a subset of the whole data set, the mini batch gradient is never going to really fully capture the whole data set gradient. But I think what they're trying to say here is that when you're doing dropout, what you're really doing is these different subnetworks, and the optimal gradient step of a subnetwork is not going to match the optimal gradient step of the whole network. What they're saying. So intuitively, this reduction in variance and error helps prevent the model from overfitting to specific batches, especially during early training when the model is undergoing significant changes. I don't know. I could see that bias variance is kind of a basic concept in statistics, but bias versus variance Gaussian. But looking for this. So this picture is shit. Here you go. So here you have some Gaussians, right? And this is the center, I suppose. This is where you want your Gaussian to be centered on. So this green Gaussian has high variance. This red Gaussian has low variance, right? In this case, the green Gaussian has high variance, low bias. And this red Gaussian has low variance, high bias. Here, both Gaussians have no bias, but this red one has low variance versus high variance. So you see this pop up over and over again, where basically there'll be this trade-off between you either get high bias or high variance. and you can only make low bias or low variance. It's kind of like similar to the ideas behind like precision versus accuracy. Yeah. So this is kind of the same concept again, this bias versus variance. So accuracy or preciseness here would refer to variance, and then accuracy would refer to bias. Approach. All right, so what do they actually do here? From the analysis above, we know that using dropout early can potentially improve the model's ability to fit the training data. Based on this observation, we present our approaches. Underfitting and overfitting. Whether it's desirable to fit the training data better depends on whether the model is in underfitting or in an overfitting regime, which can be difficult to define precisely. In this work, we use the following criterion and finding effective for our purposes. Model generalizes better with standard dropout, we consider it to be overfitting. The model performed better without dropout, we consider it to be underfitting. So I wonder what performs better mean, right? So is that performance on the test data set after a specific amount of time? Is that the best performance that is ever received or that it's ever had on the test data set? Hard to see. Regime a model is in depends not only on the model architecture, but also on the data set used and other training parameters. Yeah, and this is kind of the thing I keep saying over and over again, where these type of relationships are going to change based on the model, based on the data set, based on how you're training. So don't read too much into this. In their default settings, model at underfitting regimes do not use dropout. To improve their ability to fit the training data, we propose early dropout. Dropout before a certain iteration, and then disabling for this chaining. Late dropout. Overfitting models already have a standard dropout included. During the early stages of training, dropout may cause overfitting. To reduce overfitting, we propose a late dropout, not using dropout before a certain iteration, and then using it for the rest of training. This is a symmetric approach to early dropout. I don't know what kind of symmetry they're referring to there, but it's basically two different types of scheduling for dropout. Hyperparameters. Our methods are straightforward, both in concept and in implementation. They require two hyperparameters, the number of epochs, the wait before turning dropout on or off. Yeah, so one of the problems with kind of learning rate schedules and here dropout scheduling is that you're introducing additional hyperparameters, right? So in a learning rate schedule, you have to determine when, at what epoch, at what training iteration are you going to drop the learning rate, by how much, what's the curve for that, and right, that's just a bunch of extra hyperparameters that you need to sweep over, or you need to tune, or you need to find good values for. And if you're going to be doing dropout on a schedule, you're going to have to do the same thing again. You're going to have to figure out at what epoch you actually want to turn the dropout on or off, or I'd like to see probably a more complicated dropout schedule. It seems like they basically just turn it on and off, but I feel like you should just change the dropout drop rate P. You should be just changing this over the course of the training, right? So like if you look at learning rate schedule, right? This is what learning rate schedules look like normally, right? They're basically, I have one learning rate, and then after a certain amount of epochs, I change it to this learning rate, and then after a certain amount of epochs, I change it to this learning rate. So you're playing with the value of the learning rate here, right? So I'd be curious if they did this for the dropout too, where rather than just saying, okay, there's dropout and then there's no dropout, like play with it, right? Have a dropout of 0.1 and then have a dropout of 0.2 and then have a dropout of 0.4 and then so on. Okay, what do they have here? Classification accuracy on ImageNet 1K. So 1K here refers to the 1,000 categories. It's a classification problem with 1,000 categories. Early dropout or stochastic depth lowers the training loss. Okay, so I guess top one accuracy, which is the most difficult accuracy metric you can do. So when you're measuring the performance of a classification model, you can either say that the model needs to get the answer perfectly right, which is top 1 accuracy, or the model just needs to predict the correct answer in the top 5 guesses. And that's top 5 accuracy. So top 1 accuracy is actually the hardest one to get a good score on because the model needs to get it perfect. So here they have a vision transformer, and they show you with standard dropout versus early dropout. So actually, this is better. The early dropout does seem to perform better. You have Mixer S, Conv Next, it's ConvNet, Swin Transformer, a different type of transformer, and then VITT, which I think is a bigger transformer. What does this dagger mean? Okay, these are different implementations, I guess. Different implementations of the same transformer, or different. Maybe they're not even actually using them. Maybe they're just kind of like taking these numbers from the plots or from these papers. But kind of the more I look at this, the more I kind of see the same pattern over and over again, right? It's like basically early dropout does seem to improve the benchmark. It's by 1%, which is pretty good. Yeah, this early dropout does seem to be very good. Like, look at this, just all of these different types of models, it does better. But again, that could just be the case on ImageNet, right? It could be the case that if you tried to do this on a different data set, you would not see this pattern, and early dropout would not be better. So it's not going to be necessarily the case that early dropout is always going to be better for every single model and every single problem. It's only the case that it's better for ImageNet 1K and then in these 4 models. We conduct empirical evaluation on ImageNet 1K, right? So 1K refers to the fact that there's 1,000 different classes, right? What that means is like cat, dog, chair, couch, things like that. And in total, there's 1.2 million training images. And then top 1, again, the model has to get it 100. It has to be perfect guess in order for it to get it right. To evaluate early dropout, we choose small models at underfitting regimes, including VIT Tiny, Mixer S, Conv Next. So, okay, so they're specifically choosing smaller models that have somewhere between 5 and 20 million parameters. Okay, our drop rates are selected from 0.1, 0.2, 0.3, and 0.3, 0.5, 0.7. So different dropout rates for either dropout or the stochastic depth, which is the residual dropout. Each result is averaged with 3 seeds. So seed here refers to the random seed. So because dropout is a random process, it's going to depend on a seed, which is going to change. Seed is basically what you use to basically create a random process in a computer, and you can change if you use the same seed, the random process will be the same every time, right? And this is very useful because you want to be able to compare things, right? You don't want to have an actual random number generator. You want to have a repeatably random number generator. This means that they tried 3 different seeds, so 3 different kind of paths down the random space. Okay. Results. Table 1 presents the results. Early dropout consistently improves the test accuracy and also decreases the training loss. We doubled the training epochs and reduced mix-up and cut mix. So these are data augmentations. So this is, in the case of ImageNet, this is basically, you could think of it like just, let me just, picture's worth 1,000 word. Data augmentation, computer vision. So this is what data augmentation is. It's basically when you're training your model, you don't just feed the same image over and over again. You basically feed it slightly different versions of your image, right? You transform the images, but no matter how you transform the images, a cat is still a cat in a classification problem. So it's a way of augmenting your data set, right? Increasing the variance of your data distribution. Baselines now achieve much improved accuracy, sometimes surpassing previous literature results by a large margin. Carry out ablation studies to understand the characteristics of early dropout. Our default setting is VIT and early dropout with the improved recipe. Previous studies, different strategies for scheduling dropout or related regularizers have been explored. These strategies typically involved either gradually increasing or decreasing the strength of dropout over the entire. Okay, so maybe they are kind of doing what I was saying, where you have a more complicated schedule, right? Where you're maybe initially you have a higher dropout rate and then you basically decrease it over time. We also evaluate linearly increasing and decreasing strategies where the drop rate starts from P and ends at P over 0, okay? Annealing, curriculum. So curriculum is one way you could describe a learning rate scheduling. Annealing is another kind of term you could use to describe something like a schedule. Annealing is actually like a process you do with like metals. It has to do with heat, the way it cools down. We conduct a hyperparameter sweep for the rate of P. Results are presented. This suggests existing dropout scheduling strategies are not effective. Okay, not effective on this problem maybe, but early dropout rate scheduling. Early dropout scheduling. There is still a question of how to schedule the drop rate in early phases. In our experiments, use a linear scheduling or linear decrease schedule from an initial value of P to 0. Simple alternative is to use a constant value. It can be also useful to consider a cosine decreasing schedule. So yeah, here you go, commonly adopted for learning rate schedules. The optimal p-value for each option may differ, and we can compare the best result for each option. Table 2b presents the results. Okay. So table 2, early dropout ablation results. So this is different types of learning rates or different types of dropout schedules. So you have linear, you have constant, you have cosine, and kind of seem about the same, to be honest. I don't know, that's kind of unhype, you know. Kind of sucks. I would have thought there might have been more of a difference here, but it doesn't really seem like it makes any difference. Scheduling strategies. Early dropout outperforms alternative strategies. So these are different types of is this talking about curriculum learning? Oh, okay, no, these are just with respect to dropout rate. So you have either no dropout, you have a constant dropout, you have the early dropout, which is the one that they do in this paper where it's constant and then it becomes 0. You have increasing, decreasing, and then you have annealed in curriculum, which are just going to be more complicated versions of that. And you can see that the most performant one here is actually the early dropout, but not necessarily by much, right? Everything here is still relatively close together. And here, I guess they're looking at how model size changes whether or not it helps, right? So if you are with a tiny model versus a bigger model, right? Bigger model is going to be what they call overfitting regimes, right? Because the bigger model is going to have more capacity, so it's going to be more capable of overfitting. So you're not really going to see the big model benefit from this early dropout versus the small model does benefit. About the swag strategy. I heard got a perfect swag out of 10. All right, model sizes. According to our analysis, dropout helps model fit better to the training data. This is particularly useful for underfitting models. Our results show that early dropout is effective in improving the performance of the first two, but not effective in the case of the larger. You're seeing this overarching theme of just like large models that overfit a lot don't necessarily benefit plot the training loss and test accuracy with early dropout and compare it with a no dropout baseline. Early dropout is set to 50 epochs and uses a constant dropout rate. Training loss, dropout model is higher and the test accuracy is lower. Intriguingly, once the early dropout phase ends, the training loss decreases dramatically and the test accuracy improves to surpass the baseline. Okay, so they're looking at training curves. So here on the x-axis, you have epochs, which is basically just like training iterations, except epochs is the amount of times you've seen the same data set. Accuracy, probably the test accuracy, if I had to guess. So baseline, which means no dropout, versus early dropout, and baseline train loss versus. So this is how good you're performing on your actual training data set, and this is how good you're performing on the test data set. So test accuracy, you want it to get better over time. That's what this is, right? And this is actually your real metric. This is what you really want to be improving. Train loss is simply just how good your model is getting at kind of fitting to the training data set, right? But it doesn't, you want it to get lower over time. You want the loss to decrease, but it is not necessarily indicative of a good test accuracy. So, I mean, these plots seem very, very close together. It doesn't really seem like there's a huge difference between these lines, but you can see here, once you create this early dropout end, right? So the early dropout that they're saying after 50 epochs, they turn dropout off, and you can see how it impacts the shape, right? So going, and then dropout gets turned off, and then it goes boom, and it has like this really high increase. And it seems to go a little bit higher. So the main thing here that is useful or kind of worthwhile is the fact that this orange line is slightly above this blue line, right? So, and it gets there earlier. So all you really want is you want this test accuracy to be as high as possible. So the fact that with the early dropout, not only do you get to a higher test accuracy faster, but you also get to a higher like final test accuracy. That's a good sign. Dropout epochs. We investigate the impact of the number of epochs for early dropout. Use 50 epochs. We vary the number of early epochs and observe its effect on final accuracy. Okay, so here they change the epoch at which the early dropout happens. So you see here, the early dropout is happening at about epoch 50. So now they change it. So what if we change the early dropout to happen at 300 epochs or happen at 5 epochs? How does that change the final accuracy? And you can see how there's kind of a sweet spot here. There's a sweet spot for the epoch at which you would want the early dropout to end, right? And these kind of U-shaped curves like this are not necessarily great because what they mean is that that the hyperparameter value that is optimal is itself, there's some optimal value for it. So it's like if this chart was like this and it just went up, right? If it was just a relationship that just very clearly went up, then you would basically just want, it'd be very easy to choose a value for early dropout. You would just choose the one that you could do, the biggest possible one. But in these kind of U-shaped curves, right, the shape of these U-shaped curves is going to depend on the problem, is going to depend on the model, is going to depend on the data set. So anytime you see these U-shaped curves like that, it means that there's some optimal value for that hyperparameter, which means that you're going to have to spend the extra compute to sweep over the values of this hyperparameter to figure out what the optimal value is. Dropout rate is another hyperparameter similar to standard dropout. The impact of varying the rate is shown in figure 11. So here you're seeing another U-shaped curve here where a dropout rate of 0.1 is better than a dropout, or is worse than a dropout rate, or no, a dropout rate of 0.05 is worse than a dropout rate of 0.1, but a dropout rate of 0.1 is better than a dropout rate of 0.2. So this same kind of like U-shaped here where on either end it's worse than in the middle. Here you have dropout versus the stochastic depth, which is the residual dropout that they described earlier. Learning rate warm-up. Learning rate warm-up is a technique that also specifically targets the early phase of training, where a smaller learning rate is used. We are curious in the effect of learning rate warm-up on early dropout. Okay, so what if you combine learning rate scheduling and early dropout, right? Is that going to mess things up? Our default recipe uses a 50 epoch linear learning rate warm-up. We vary the learning rate warm-up length from 0 to 100 and compare the accuracy with and without early dropout. Okay, so here they're changing the learning rate warm-up is going to be similar to this early dropout type of idea, where there's going to be a specific epoch where you change the learning rate. So here they're saying, at what epoch do I stop doing this learning rate warm-up, and how does it compare? How does it affect the early dropout? And you can see that there is some kind of relationship here, right? It's not huge, right? The difference between this 76, 76, and 70, these are close together, but they're different, right? So there is some kind of interaction happening between the learning rate warm-up and the early dropout, and finding an optimal value for both of those is going to be very tricky. Late dropout. Okay, so up until now, we've only been talking about early dropout, but you could also do a late dropout, which means that you're not doing any dropout, and then after a certain point, you do a late dropout. So they've also been doing all their early dropout stuff. They've been doing it with small models, and now they're going to be doing it with big models. And the reason they're doing this is because I think they're going to tell you that the late dropout is going to prevent the overfitting that is characteristic of large models that have a large capacity. And these models are considered to be in the overfitting regime. All right, so here you have VITB, which is a bigger version of the transformers that we were looking at before. See how with late dropout, you seem to get a little bit of performance boost. But these are really small, right? You're talking about 81% top one accuracy versus 82% top one accuracy. Demonstrating that late stochastic depth effectively reduces overfitting. We also compare results with a linear increase in a curriculum schedule with the best P over hyperparameter sweep brings a larger. Okay, downstream tasks. We evaluate the pre-trained ImageNet 1K by fine-tuning them on downstream tasks. Okay, so now rather than just evaluating on ImageNet 1K, which is a classification task, they're going to pre-train on the ImageNet dataset, but then they're going to evaluate the model on a different type of benchmark. So something like object detection on COCO or semantic segmentation on ADE20K. So these are benchmarks, right? These are data sets. COCO is a data set. Object detection is a task. So by testing this ability to transfer from one task, which is ImageNet classification, into object detection on COCO, you're kind of measuring how general the model is, right? Like, how useful are the representations that you've learned? How general are they? Do they also apply to a different task in a different data set? So it's a way of measuring kind of the generalization ability of a model. So let's see what they get. So COCO object detection, of course, object detection, you're going to measure with average precision, and then box refers to the fact that it's a bounding box. Of course, if you have segmentation, it's going to be a mask, not a bounding box. And then this number here, 50, 75, this is the intersection over union, which is how much IOU computer vision. So basically, how good does your bounding box need to be in order for the detection to count, right? So here, any box that is within 50% IOU counts as a correct answer. Any box that's at a 75% IOU counts a correct answer. So this is a more lenient metric than this one. That's why the score here is worse than the score here. Same thing here, right? With mask segmentation, 75% IOU versus a 50% IOU is going to be harder to achieve. So it's kind of like the difference between top 1 accuracy and top 5 accuracy. But I'm kind of digressing here. Largely, I think what they want to show us here is that with the early dropout, you are getting better performance on this separate task. So there is an advantage to using dropout in order to increase the generalization capability of your model. Okay. They also tried on a couple different classification tasks, CFAR, flowers, pets, STL10, 101, all these different classification data sets. Notice how they're all in the same kind of period here, 2009, 2008, 2012, 2011, 2014. It's like as soon as you had like phones, right? Like phones, and people started taking pictures with digital cameras, and you started to have this kind of explosion in the amount of image data that was available, right? That's when you got all this stuff. And it's, people kind of myopically focus too much on things like dropout and convnets and so on, when really it's cell phones and digital cameras and the availability of large data sets and GPUs and so on. So like the hardware is really what's driving advances in deep learning. It's not the model architectures. It's not the software, right? Like people were using convnets and dropouts. People were doing this stuff for decades and it wasn't leading anywhere. It was really when you started to have very low cost cameras, very powerful GPUs, the internet. Related work. Okay, so this is interesting. I've seen this a couple times now, but basically related work, sometimes this section in most papers is right after the introduction, but I keep seeing this over and over again in more recent papers where they just kind of stuff the related work at the end, which is fine because usually the related work is kind of like not super readable. It's like you see here, look at all these citations, right? In the related work section, it's just like sentence after sentence just describing other work that people have done that's like somewhat related or could be seen as being related, and then it just ends up being this giant mess of citations that doesn't actually get you anything. But the reason it's very important is because academic people and professors, they're largely evaluated on the number of citations they have, right? So if you write a paper, you want that paper to be cited in as many future papers as possible, because if your paper is very good, a lot of people are going to cite it. So related work section is important because academics need citations in order to basically raise more money and continue to kind of do their research, right? It's like a metric that they use to evaluate themselves. But it also means that there's all kinds of politics and shady stuff going on with the citations, right? And these related work sections, one thing that you see all the fucking time is whatever group here. So like, where is this group from? This team is from Facebook AI Research. So I bet you if you go here into the related work section, there is an overabundance of Facebook AI research papers, right? And papers of people who now work at Facebook AI Research. So there's a little bit of kind of like you shake my hand, I shake your hand, or you pat my back, I pat your back when it comes to this related work stuff. And people kind of like pad their citation numbers with that. And not only that, but it also makes double-blind review difficult, right? So whenever people are reviewing papers, you ideally want to be reviewing it for the quality of the work, but sometimes what people will do is they'll just go into these related work sections and they'll say, okay, what are all the citations that they're doing? Okay, they're all citing Google work. Oh, okay, this must be a Google paper. Okay, well, if it's a Google paper, I'm just going to rubber stamp and say, yep, this is fine. It's probably fine. So a lot of shady stuff that happens with the citations, and I wish it wasn't as big of a part of papers and academic culture. Okay, so what are they stating here? Weight decay increases. L1 regularizations can promote sparsity. Label smoothing replaces one-hot targets. Data augmentation as a form of regularization. Other types of data augmentation: hide and seek, cutout, random erasing. Different types of dropout. So drop connect, variational dropout, spatial dropout, drop block. Look at that. Applying dropout for compressing, and a survey paper on dropout. Scheduled dropout, so curriculum dropout. NASNet, this is neural architecture search. Efficient net v2. AP is such a strange metric. I've tried to understand it, but in Cocoa they describe some strange 101 step interpolation done on precision recall curves. Any useful interpretation? So AP is average precision, but Theo, I'm going to come. This might not be exactly the answer that you want, but here's what we're going to do. Explain AP in the context of computer vision performance metrics. I want you to explain it to me in the simplest way possible. I am a streamer reading a ML paper online, and I want my whatever, leave it there. Let's just do this. AP stands for average precision, a popular performance metric used in computer vision to evaluate the accuracy of object detection. AP is used to measure the precision of the model at different recall levels. Precision is a measure of how accurate the model's predictions are, while recall is a measure of how many objects the model can detect. AP metric takes into account both precision and recall to provide a single number that summarizes the model's performance. Yeah, and I think this is what you're kind of getting to, Theo, is that like there's certain applications where precision is more important, and there's certain applications where recall is more important. And by combining both precision and recall into this kind of like combined metric of AP, you're kind of losing the specificity of like what a metric is supposed to give you, right? A metric is supposed to tell you, is supposed to let you compare two different things, right? So you can compare things and say, okay, this one's bigger, this one's not bigger, and so on. But if the metric itself is kind of this like aggregate metric, like what is it becomes harder to interpret. And then if it becomes harder to interpret, that kind of loses the whole point of what a metric is supposed to do, right? A metric is supposed to allow you to easily interpret and compare. To calculate AP, we first calculate precision and recall values for the model at different confidence levels. Okay, so confidence level with anything like a classification model or a bounding box or something like that, there's going to basically be a confidence. Sometimes these are called logits. People interpret them as probabilities, right? It's basically like how strongly is the neuron that is associated with cat firing versus the neuron that is associated with dog firing. Or whenever you get a bounding box, is that a bounding box where the neuron that classifies it as a cat is like very, very high fire or very low fire, right? Then we calculate the area under the precision recall curve, which gives us the AP score. Higher AP score indicates better performance, meaning that the model is better at detecting objects while minimizing false positives. So, yeah, I don't know. Maybe this becomes another thing that I rag on. You know, I love to rag on Frechet inception distance and clip score as a measure of image generation quality, but maybe, Theo, I should also be ragging on AP as a measure of object detectors. Why don't people like to use AP in their papers? Let's see if... However, there are some potential reasons why some researchers might prefer other metrics. Complexity. Yeah, this is what I was saying, limited interpretation, where it's like, I just feel like because it's like this aggregate metric, it just becomes more complicated and unnecessary. And it's like, you don't really know what the fuck is actually, what it's actually saying. Inconsistency in implementation. So this is more what you're saying, Theo, where there's different ways to calculate AP. So different packages, different PyCoco and all the different tools are going to have different ways of calculating AUC. So you're going to see different numbers and they're not going to be the same. AP is sensitive to the threshold that is used to define a detection. So the threshold is this number here, right? The 50 or the 75, that's the threshold. AP remains widely used and a respected metric in computer vision research. Many researchers continue to use it to evaluate their model's performance. I don't know about computationally expensive. You can do it on the CPU, so it's easy money, right? As long as you don't need to use a GPU, it's probably fine in terms of computation. CPU instances are way cheaper than GPU instances. Yeah, look at that. ChatGPT, it's better at computer vision than all of us. Okay, where were we? We were in the related work section here. Yeah, different types of dropout scheduling. So anneal dropout, curriculum dropout. Our approach differs as we study the dropout's effect and blah, blah, blah. Yeah, this is kind of another annoying thing about the related work is that you always, the author always has to like somehow validate or somehow like argue that the particular thing that they're doing in their paper is different enough from everybody else's papers, you know? Which I think is unnecessary. I feel like we should be more okay as a scientific community with people doing the same work, right? Like I wouldn't mind if there was another paper that basically did exactly what this paper did. That's totally fine, right? It's like having multiple papers that do the same thing is actually that's what reproducibility means, right? It's like you want different research groups to do the same work and you hopefully want to see that the results they get are the same. But there's such a pressure to do something novel, right? Novelty. You want to be doing something different than anybody else. That this pressure for novelty, like, I think is part of the reason why you have a reproducibility crisis because nobody wants to spend any time reproducing anybody else's work, right? It's like all they want to do is they want to convince you that what they're doing is different from what everybody else is doing and that there's no way you should think about their stuff as the same as somebody else's stuff. So, no. Maybe I'll stop waxing poetic about academic institutions and misaligned incentives. Let's see the conclusion here. Dropout has shined for 10 years for its excellence in tackling overfitting. We unveil its potential in aiding a stochastic optimization and reducing underfitting. Our key insight is Dropout counters the data randomness brought by SGD and reduces gradient variance at early training. This also results in stochastic mini-batch gradients that are more aligned with the underlying whole dataset gradient. Motivated by this, we propose early dropout to help underfitting models fit better, and late dropout to improve the generalization of overfitting models. We hope our discovery stimulates more research in understanding dropout and designing regularizers for gradient-based learning, and our approaches help model training with increasingly large data sets. Cool, cool, cool. What do they have here? Experimental settings. Yeah, I feel like I would have wanted to see more aggressive dropouts. So like what happens if you have a dropout of 0.8? Like that would have been interesting. Maybe different types of optimizers too. So I know Atom is super popular, but it would have been curious to see what it looks like with some of these other optimizers, you know? Another kind of U-shaped curve here for the late dropout. Okay, so the Roomba is encroaching upon my room, so pretty soon all you're going to be hearing is that Roomba vacuum, but I'll stop there. Hopefully this was useful. It was fun. Thank you for the questions, guys. Theo, especially, thank you for being engaged and asking questions. Love to hear that. Definitely feel free to join our Discord if you want to talk. I try to answer any questions on there the best I can. If not, like and subscribe as always. Thanks for listening, and see you guys later. Happy learning.